All right, so capillary forces are the surface tension that exists in the liquid, vapor interface can be used to actually draw liquids up columns of things, or not necessarily in columns. It could be like in the pores of porous things like paper towels and things like that. So those are called capillary forces, and they can be used to draw liquids against gravity or just in horizontally, whatever you want. So that's called capillarity. So let me do like a little example to show you like how you would calculate how far a column of liquid can be drawn up a capillary. So a typical type of thing to do would be to create a free body diagram. So in the left picture here, I'm showing it's almost like a little tube that's been inserted into a reservoir of water. So I'm going to imagine that it's like a glass, like a glass tube. Water is very strongly attracted to the sides of glass, so the contact angle is less than 90 degrees, which creates so if I think about, right at the edge of where the liquid contacts the solid, there's a surface tension force. So that's so in the case of water, that'd be like almost 72 millinewtons per meter. So you've got a force per unit length acting around the contact excuse me, the contact perimeter where that liquid touches the glass tube. And that force will generally try to pull the column of liquid upwards. And against that is acting gravity that is pulling that column of liquid back downwards. And so if you make a free body diagram, you basically get, a distributed line force that's pointing at an angle that's equal to the contact angle. That's all pulling upward. And then there's density times volume is a mass. Mass times gravity will give you a weight of stuff pulling downward, right? So if you do that force balance, so sigma times cosine theta is the upward force per unit length along the perimeter of the contact line between the liquid and the solid, and the actual perimeter is 2 pi r. And that upward force caused by surface tension is balanced by the gravitational force pulling all the liquid in the column back down. So if I assume that not much of the liquid is contained in that little curved region at the very top, then that volume would be the density times, pi r squared h is the volume times gravity pulling it back down. And you can solve that for h, and you get, I don't know, whatever equation I have written here. I guess it's sigma cosine theta divided by rho g times the radius of the tube, the inner radius of the tube.